Welcome to the video lecture on the first derivative test. The first and second derivatives of a function are tools of calculus that give information about the shape of a graph that is useful for finding maximums, minimums, and graphing. Now when we're doing our first derivative test, we're going to be learning about a test that tells us when a graph has maxes and mins, and also where a graph increases and decreases. So let's start by talking about the definition of an increasing function. So increasing means that a graph rises from left to right. If A is less than B, then f of A needs to be less than f of B. So that would mean if A is to the left of B, then f of A needs to be lower than f of B. Now notice, if we were to sketch in all of these little tiny tangent lines, notice that every single tangent line there slants up to the right, which means it has a positive slope. And what are these slopes? They are called the derivative. So what we're going to notice is that a graph is considered increasing if its derivative is positive. Now if we look at the definition of decreasing, a graph decreases if it falls from left to right. So if we have A less than B, then f of A needs to be greater than f of B. So if A is on the left and B is on the right, then f of A needs to be higher than f of B. And if that happens, we say the graph decreases. If we sketch in all of these little tangent lines, notice that each of these falls. So that means they have a negative slope, and slope is the same thing as a derivative. So this means a graph will be decreasing if its derivative is negative. So this is a theorem. It says if f prime of x is greater than 0 for all your x's in your interval I, then f increases over that interval I. If your derivative is less than 0 or negative for all the x's in your interval I, then f is decreasing over that interval. We say that a function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. And what we want to notice is that a function can only change from increasing to decreasing at critical numbers or critical points. Now remember what a critical point is. A critical point is a place where your derivative is either 0 or d and e. So if we look at this graph right here, right at this little peak, we have a horizontal tangent line. And we know that the slope of a horizontal line is 0, so that means the derivative is 0 right at that peak. Now to the left of that point, if we sketch in all of these tangent lines, they're all slanting up, and that's because our graph is increasing on that left side. So these derivatives are positive on the left, which is why our graph rises. But on the other side, if I draw in these tangent lines, all of these lines fall, so our derivative is negative and the graph decreases. So the only way that the graph can go from rising up to falling is if it hits that 0 in between. Likewise, for this shape here, this U shape, we have another horizontal tangent line right at that minimum, so we know that the slope or the derivative there would be 0. On the left side of that horizontal tangent line, all of these little tangent lines are falling, so their derivatives are negative and the graph decreases. On the right side, all of these tangent lines rise up, so your derivative is positive and the graph increases. So again, I can't change from a negative derivative to a positive derivative without hitting 0 in between. Now in this last one, I have all of these tangent lines are rising up, so I have positive derivatives on the left, so the graph rises up, and then on the right side, all of these derivatives are falling, so the slope is negative and the graph decreases. Now this time I'm going from a positive to a negative, and at this little kink in our graph, what is the derivative doing right there? Well, what we know is that kinks or sharp turns in our graph are derivatives that do not exist. So the only way we can change from positives to negative slopes is either hitting zero in between with your derivative or having a derivative that does not exist. And the same is true from going from a minus to a plus. I can't decrease and then increase without either hitting zero or being D and E. So these critical points are really important. So here's a typical example. We want to find the intervals of increase and decrease for the following function. So since those critical points are really critical, they are the things we want to find first. And critical points are going to be where your derivative is 0 or D and E. So let's start by finding the derivative of this function, just by using my power rule. Derivative of 12 goes to 0, derivative of 9x is 9, derivative of minus 3x squared would be minus 6x, and the derivative of minus x cubed would be minus 3x squared. Now, critical numbers are going to be where this derivative is either 0 or D and E. Since this is a nice quadratic function, this would never be D and E. Usually you're only going to get a derivative that's D and E if you're dealing with a fraction and that denominator might become 0 to make it undefined. So let's just find out where this quadratic equals to 0. Now if we're lucky, this will factor. So what I'm going to do first is notice that there's a GCF. All of these numbers are divisible by 3. And something else that I don't particularly like, and this is just my preference, I don't like leading off here with a negative x squared. So I'm actually going to factor out a negative 3 from all of my terms. So that means I would have to have a negative 3 left over, a positive 2x, and a positive x squared, so that if I were to redistribute, I would get back exactly the right signs. So all of my signs switched inside here. Now to make factoring easier, I'm going to put this in descending order. So this is the same as x squared plus 2x minus 3. Now if I'm lucky, it'll factor. So 2 sets of parentheses, I need an x and an x. And if I make this a 3 and this a 1, and make the 3 positive and the 1 minus, I'll get a negative 3 on the end, and my middle terms will add up to a positive 2. So this does work. Now the negative 3 does not have an x, so it doesn't contribute any solutions. But this factor will give me negative 3, and this factor will give me positive 1. So my two critical numbers are going to be x equals negative 3 and positive 1. So here's what we're going to do, and this is a strategy that you'll be using quite a bit in this chapter. We're going to create a number line. This is going to be a number line for the first derivative, and what I want to put on that number line are these two critical numbers that I just found, and you want to put them in order. So we're going to do negative 3 on the left and positive 1 on the right. And I always like to write down next to this number line which derivative it's for, and I'm going to write down its rule. And the rule that I want to write down is the most simplified, most factored rule that I came up with, which for me was right here. So I'm going to write down negative 3, x plus 3, x minus 1. And now what we're going to do is realize that based on what we talked about before, the only way that a function can change from going from increasing to decreasing or vice versa is at critical numbers. So that means if I only have these two numbers for my critical numbers, then everywhere here in the middle or to the right of 1 can only be strictly increasing or strictly decreasing. It can't change in between. So what I'm going to do is test a number, any number at all, from each of these three intervals and determine whether or not my derivative is positive or negative, and that will tell me whether I increase or decrease. So we're going to pick a test point. I'm going to start over here on the left, and you can pick anything you want as long as it's smaller than negative 3. So I'm going to try negative 4. And what I'm going to do is go over here, and I'm going to plug it in to this factored derivative. Now, I don't really care about what size this answer is. I just care about its sign, whether it's positive or negative. So don't do all the work of actually figuring out the number. Just do the work to figure out whether it's plus or minus. So for example, negative 3 is obviously negative. If I take negative 4 and plug it in this middle factor, negative 4 plus 3 is negative. And negative 4 minus 1 is negative 5, so that's also negative. And we're multiplying these together. So 3 negatives multiplied together stay negative. So this would be a minus sign right here. Now let's do the exact same thing, but this time in the middle. So pick any number as long as it's between negative 3 and 1. So maybe 0. Now negative 3 obviously is still negative. 0 plus 3 is now positive. 0 minus 1 is negative. Two negatives become positive, so this middle interval becomes positive. And finally, let's pick something over here on the end, maybe 2. Negative 3 is still negative. 2 plus 3 is positive 5. 2 minus 1 is positive 1. So we have only one negative, so this is going to be a minus sign. Now what does this tell us? Well, remember from our theorem up earlier, a function will increase if its derivative is positive, and a function decreases wherever its derivative is negative. So right here in the middle, I have a positive derivative. And we want to write out all those x's that represent this interval. We're going to use interval notation. So that all the x's in here would be from negative 3 up to 1. And notice that I'm using parentheses around those endpoints because at negative 3 and 1, at those critical numbers, we're not technically increasing or decreasing. Now to the left of negative 3, I had a negative sign, so that means I'm decreasing over here, and that would be the interval minus infinity up to negative 3. And over here to the right of 1, that would be from 1 to infinity. And I want both of those, so I'm going to put a union in between. So here are my intervals of increase and decrease. Now recall that critical points are candidates for relative extrema, but they may not necessarily be relative maxes or mins. And we're going to create something called the first derivative test to determine whether or not we have a relative max or a relative min. So we're going to find out where they occur and what kind they are. So here's a relative min. Now notice that to the left, again, we have those tangent line slopes that are falling. So the derivative would be negative, and our graph is decreasing on the left side. On the right side, all of these slopes are positive, so the graph is rising. So what we would see on our number line for the first derivative is we would have that critical number c listed on our number line, and to the left we should see minus signs because we're decreasing, and to the right we should see plus signs because we're rising. So I'm going down and then up, and that is why I have a relative min at c. So what would happen if I have a relative max? Well, on the left side, all of these slopes are positive, so my graph is rising, and on the right side, all of these slopes are negative, so I'm decreasing. So my number line should look like C, and on the left of C, I should see a plus sign for all these rising slopes, and on the right side, I should see a minus sign. So it's like I'm rising up on the left and falling on the right. So we have a relative max at x equals to c. Now what happens for these two? The graphs obviously do not have little maxes or mins, so there's no relative max or min here. And the reason for that is because if you think about these slopes, they're entirely positive on both sides of c for this first graph. So your number line would look like plus on the left and plus on the right. Whereas on this example, all of these slopes are falling, so your derivative is constantly negative on the left and on the right. So if you get a number line where the signs do not change, either they're plus plus or minus minus, then you will not have any relative max or min at that particular critical number. So this is called our first derivative test. If you have a continuous function that has exactly one critical point in an interval a to b, then that critical number will be a relative minimum if the derivative changes from a negative to a positive. And that's because we're falling on the left and rising on the right. That critical number will be a relative maximum if your first derivative changes from a positive to a negative, so that I rise up and then I fall. And you will have no relative max or relative min if the derivative doesn't change signs. So if it's plus plus or minus minus, then we're out of luck. Okay, so let's go ahead and try our example that we used earlier, that cubic function, and this time we're going to use the information that we just figured out to figure out a nice graph or sketch of this function. So let's recall what the number line looked like for this particular function. We already did all the work on the previous page. We had two critical numbers, one at -3 and one at 1, and our signs were minus, plus, minus for that first derivative. So based on this, we knew that we increased in the middle and we decreased on the two ends. Now what does this tell us now using that first derivative test about the maxes and the mins? So let's look at the change in signs. At -3, I'm negative on the left. That means you're falling on the left and then you're rising on the right. So that is a little minimum right there. So we have a relative min when x is -3. If we look at 1, we're positive on the left, which means we're rising on the left side of 1, and then we're negative on the right, which means we're falling after the 1. So here we have a relative maximum. So we have a relative max when the x value is 1. Now we're going to be graphing these. So when you graph, it's always a good idea to know the x and the y coordinates because we need to plot these points. So the x's we know from the critical numbers. How do we get these y coordinates here? Well, you always can find your y's because your y's are your function. You always want to go back to the original function to find your y values. So to find the y value when x is -3, I would just plug in -3 for all of these x's. So 12 plus 9 times -3 minus 3 times -3 squared minus -3 quantity cubed. Make sure you're using parentheses when you plug that in. And you can do that on your calculator and it turns out to be -15. Now to find the y coordinate when x is 1, then I would just be plugging in 1 for each of these x's. So 12 plus 9 is 21, 21 minus 3 is 18, 18 minus 1 would be 17. So far, if I want to make my graph, I can plot two key points on that graph. We have our relative min at -3, -15. So I'm going to go -1, -2, -3, and I'm going to have a scale of 5. So -5, -10, -15 on that y-axis. So here would be my relative min. And then at 1, 17, we have a max. So 5, 10, 15, and I would be just a little bit above that at 17. Now when you're making a graph, it's kind of nice to know some of your intercepts as well. So use that information to help you plot a few extra key points. And if you're ever unsure, you could always plot additional points by just picking any x that you wanted, plugging it in and finding the y. So if you're not sure or you just want a few more details in your graph, you could always plot more points. I like to look at intercepts if they're easy to find. The x-intercept would occur when y was 0. And that would actually be fairly difficult to solve because we have a cubic equation. So I'm not going to bother trying to find the x-intercept, but I will find the y-intercept. The y-intercepts are usually always easy because all you have to do is let your x be 0. So this x would be 0, this would be 0, this would be 0, so the only thing I'd have left is that 12 for y. So that means I have a y-intercept at 12, which means it's going to hit the y-axis right about here. Now based on that, and based on our number line over here, we know that to the left of -3 we're decreasing. So I have to be falling into that minimum on the left side of -3. Then I have to increase up to this maximum at 1, and while I'm increasing, I'm going to be going right through that y-intercept. And then after the 1, I have to fall again, so I would have to decrease just like that. So here's a very rough sketch of my graph. All right, let's try that again on another example. So this time we have the function 5 over x squared plus 1, and we want to find the relative extrema, that means relative maxes and relative mins, and then we want to put it together into a graph. So number one place to start is your derivative so that you can find those critical points, because those are going to be the places where you have your relative maxes and mins. There's no other places. So to take the derivative of this, you can certainly use a quotient rule, nothing wrong with that. I'm going to be a little bit clever here, and I'm going to rewrite this as 5, and then I'm going to take that x squared plus 1 and move it up to the numerator by giving it a power of -1. And then I'm going to take my derivative. I haven't done the derivative yet, so let's do the derivative next using the chain rule. So I would leave the 5 where it is, bring down my power. When I subtract 1 from the power, the new power becomes -2. What's inside stays inside, and then I have to multiply this by the derivative of that inside, which would be 2x. So when we simplify, 5 times -1 times 2x is -10x. And I'm going to go ahead and take this x squared plus 1 and move it down to the bottom with a +2. So here's my nice cleaned up derivative. So critical numbers will occur wherever this is 0 or d and e. When does a fraction equal to 0? Well, a fraction is only going to be 0 when its numerator is 0. So that could happen if -10x equals to 0, and that's obviously going to happen if x is 0. How about where does it become d and e? Well, a fraction becomes d and e whenever you're trying to divide by 0. So to find out where this fraction is d and e, I'm just going to take that denominator and find out if it ever equals to 0. Now this quantity squared will only equal to 0 when that x squared plus 1 part is 0. And you could probably see it from here, but if you subtract 1, you would want to then take a square root, and that would cause us to take the square root of a negative number, which is not a real number. So we're not going to worry about imaginary numbers in this course, and that means we do not have any places where this derivative is d and e. So the only critical number we got was this x equals 0. Okay, now once you have your critical number, you're going to make a number line. And I only have 0 to put on it. And I'm going to label my derivative over here with the most cleaned up factored version of my derivative that I have. And that is right here. So -10x over x squared plus 1 quantity squared. So if we test to the left of 0, we could put in anything we want, but I'm just going to use -1. And I'm going to test it over here. -10 times a -1 would be a +10. And notice that denominator, no matter what you plug in for x, you're going to square it, and then you're going to add 1 to that, and then you're going to square that again. So that is always a positive value. There's nothing you could plug in down here that would ever make this become negative because of that outer square. So that denominator is always positive. So we get a plus over a plus, which stays plus. So this is positive. Now let's test to the right of 0, so let's try 1. Negative 10 times 1 will be negative 10, so that'll stay negative, and the bottom remains positive always. So a negative divided by a positive is going to be negative. Now this number line tells me 4 things right away. It tells me where my graph increases, where it decreases, where I have any relative maxes, and where I have any relative mins. So this is a powerful piece of information right here. Wherever you see plus signs on your derivative, that's where the function increases. So this would be the interval minus infinity up to 0. Anywhere where we see minus signs is where we decrease. So that's going to be on the other side from 0 to infinity. Make sure you're using parentheses. Now we want to use that first derivative test. So if we look at the sign changes here, I go positive then negative, which means I rise and then I fall. So that means I have a little max going on. So we have a maximum at 0. And that's the x value of that maximum. Because 0 was my only critical point and it's a max, then that means I don't have any relative minimums. Okay? Now what is the y coordinate of this max? To find your y values, you always go back to the original function. If I were to plug in 0, 5 over 0 plus 1 is just going to be 5. And that is also, by the way, a y-intercept right there. So I don't even need to bother trying to find the y-intercept. I already know what it is. So let's try plotting our points. The only point I know is 0, 5, and I know it's a max. I know that I have to rise up on the left of 0, and I have to fall on the right side of 0. Now before we just let this continue all the way down, take a look at our function right here. This is a rational function, and we have talked about rational functions in previous lectures. They have a predisposition towards having asymptotes. Now this one doesn't have any vertical asymptotes because that denominator was never going to hit 0. Remember, we talked about that over here. But this does have a horizontal asymptote. And the way we figure out horizontal asymptotes formally is we look at what happens in the limit as we go to plus or minus infinity. So think about what this would do. If x gets really, really large, then this denominator is really, really large. And the top is a fixed constant. And a fixed constant over something that's getting bigger and bigger and bigger is going to get smaller and smaller and smaller. So this is going to go to 0. And what that tells me is that I have a horizontal asymptote at y equals to 0. So there's like an imaginary horizontal line along that x-axis that I approach as I go really, really big to the right and really, really big to the left. So this is going to approach it just like that. And I don't ever cross it because this function is always a positive value because of that x squared plus 1 in the bottom. This can never become negative. So this is, again, just a rough sketch of our graph. Let's try another one. Okay, this time we have the function x plus 3 raised to the 2/3 minus 5. So we want to find the relative extrema and graph the function. So just like before, the first place to start is your derivative. And this is going to be a derivative that I can find using my chain rule. I have this outer power. So I'm going to bring down my 2/3, and I'm going to subtract 1 from the power, which will leave me with a negative 1/3 power. What's inside stays inside. The derivative of that inner function just wants to be a 1, so I don't even need to write that. And the derivative of my minus 5 goes to 0. So that doesn't need to be written either. So here's my derivative. Let's just clean it up a little bit. I have a 2 on top. I've got that 3 on the bottom. And since this is a negative exponent, I'm going to go ahead and flip it back down to the bottom. And if you want, you can realize that that 1/3 power really means a cube root. So this is really what our derivative is looking like. So critical numbers. Where is this going to be 0? And where is this going to be d and e? Well, the only place a fraction is 0 is when its numerator is 0. And this numerator is always 2, so that can't happen. The only place where a fraction becomes undefined is when its denominator is 0. So that can happen here. When does 3 times the cube root of x plus 3 equal to 0? Well, if I divide by 3, then I need to know when that cube root of x plus 3 will be 0, and that's only going to happen when that inside stuff is 0, and that would happen at -3. So the only critical number that I have is at x equals -3. So let's make our number line. F prime, the only critical number I have is -3, and my most cleaned up, nice derivative is right here. So let's label this 2 over 3 times the cube root of x plus 3. And now we're ready to test our points. So I want to test something less than -3. So maybe -4. If I plug in -4, the top is always a +2, so that numerator is always a plus. In the bottom, -4 plus 3 is -1. Cube root of -1 stays negative, and when I multiply that by a +3, it's going to stay negative. So this quotient will be minus. So we have a minus sign on the left. Now let's try something on the right. So anything bigger than -3, maybe 0. The top is again that +2, so that'll be plus. 0 plus 3 is positive. The cube root of a positive stays positive, and we're multiplying by a +3, so that denominator is positive, which means this quotient is positive. So those are my signs. Now we're ready to write down our 4 pieces of information. Where does it increase? Where does it decrease? Where's my relative max? And where's my relative min? So the plus sign is where I increase from -3 to infinity. My minus sign is where I decrease, so -infinity to -3. If we look at our sign changes, I'm negative on the left, so that means I have to fall, and I'm positive on the right, so I have to rise, which means right at -3 we have that little dip, which is a minimum, and that's the x value, -3. Since I only had one critical number and it was a min, then I must not have any maxes. Now how do I find this y value? Well, we go back to our function. -3 plugged in is going to give me -3 plus 3, which is 0, and 0 minus 5 is going to be -5. So we want to plot what we know here. We've got only one point, -3, -5, and that's not a whole lot to go on. So I'm going to go ahead and go back to my function up here, and I'm going to go ahead and find some intercepts. So let's find the x-intercept first. That happens when y is 0. Remember, your y is on this side, so we're going to put 0 on the left side, and that means we have to solve this for x. Now normally that might be tricky to do, but we can actually do it on this one. We can add that 5 over to the other side. And in order to get to that x, we have to get past this 2/3 power. So how do I undo a 2/3 power? Well, the easy way to do that is to raise both sides to the reciprocal power, 3/2. The reason why that works is because on the right side you have a power to a power, so you multiply, and 2/3 times 3/2 is just 1. So the right side is just like an x plus 3 to the 1. The left side is now 5 to the 3/2. Now, technically, what I was doing when I raised both sides to the 3/2 was I was taking a square root and then cubing, because that 2 in the bottom means a square root. And remember, when you take a square root, you technically get 2 solutions, plus or minus. So I really need to have that plus or minus symbol in there. If I finish solving for x, I would get -3 plus or minus 5 to the 3/2 equals to x. And that's a little messy. You'd want to dig out your calculator for that. when you do the plus case, negative 3 plus 5 to the 3 halves is equal to approximately 8.18. And when you do negative 3 minus 5 to the 3 halves, you get approximately negative 14.18. So we have an x-intercept at a little over 8. So right about there, and then also at negative 14. So right over here. Now that was my x-intercept, so let's find our y-intercept. So going back to my function, to find a y-intercept, you let x be 0. So we're going to put a 0 right here. And that would just give me 3 to the 2/3 minus 5. So we let x be 0, and we get that y is 3 to the 2/3 minus that 5. And if you do that on your calculator, that's approximately negative 2.92. So just about at negative 3. We have a dot on the y-axis. All right, now we have a few more points. We have our graph needing to increase or rise up on the right side, and it's got to go through those two intercepts. And on the left side, we want to decrease, so we need to fall into this point. And notice here, I purposely, my graph is a little bit crooked here, but if I look at that negative 3 for a moment, what did we know about the derivative right at negative 3? That negative 3 was determined by looking at where this derivative was dne, does not exist. And what happens on a graph if you have a derivative that is dne? That is actually a graph that has a kink in it. So that's why you want to kind of make your graph have sort of a sharp turn or kink or cusp in your graph right at that negative 3. You don't want it to be nice and rounded. You want it to be pointy. So here's what my graph looks like. As we learn more skills and more information in future lectures, we'll be able to get a little bit more detailed of a graph and have a little bit more idea of exactly how to draw this. But for now, we're just going to base our graphs on maxes and mins and where it increases and decreases, and occasionally finding some extra points like those intercepts. Okay, on this last example, we're going to do the same thing again, but this time we're going to do it with the trig function. So here my function f is sine x times cosine x, and we want to find the intervals of increase and decrease and the relative extrema on the intervals 0 to 2 pi. So always start with that first derivative, f prime of x, to find those critical points. Now be careful here. This is sine of x times cosine of x. So you must use a product rule when you're taking the derivative. So we're going to do first times the derivative of the second plus the second times the derivative of the first. So the first is sine of x times the derivative of the second. The derivative of cosine is minus sine of x, plus the second, which is cosine, times the derivative of the first. The derivative of sine is cosine. Now let's clean it up. I'm going to pull that negative out front, and this is negative sine squared x plus cosine squared x. Now, if you rearrange these terms slightly, I'm just going to use that commutative property and put the cosine squared in front. This should look vaguely familiar to you because this is a double angle identity for cosine. And it's going to probably behoove you to change this to cosine of 2x because it'll be easier to work with having just a single function here instead of having two separate functions. Now when we're trying to find our critical numbers, we're trying to find out when this is 0 and when this is dne. Now cosine never becomes undefined, so we don't need to worry about that, but we do need to know where cosine of 2x will hit 0. So think about this for a moment. When does cosine of an angle hit 0? What does this angle need to be? Well, cosine hits 0 at pi over 2 and 3 pi over 2 and so forth. So this angle, this quantity 2x, needs to be pi over 2 plus 2k pi, or 3 pi over 2 plus 2k pi. Now we're not done solving for x yet because we have to get rid of this 2. So I'm going to divide everything by 2. This, the pi, the 2k pi, this one, and this. Okay, so we'll end up, if we simplify this, with a pi over 4 plus k pi, or a 3 pi over 4 plus k pi. Now that's an infinite number of possibilities, but we're lucky in that we're only looking at the interval 0 to 2 pi. So what are these critical numbers going to be that lie between 0 and 2 pi? Well, if k is 0 here, then we would just get pi over 4. And if k is 0 here, we would get 3 pi over 4. If k is 1, pi over 4 plus pi is pi over 4 plus 4 pi over 4, or 5 pi over 4. And if I let k be 1 here, 3 pi over 4 plus pi is 3 pi over 4 plus 4 pi over 4, or 7 pi over 4. And these are actually all the pi over 4 angles in each of my 4 quadrants. So if I were to let k be 2, then I'm going to be outside of this interval. So I can stop here. All right, now that I have my critical numbers, we're ready to make our number line. So I have pi over 4, I've got 3 pi over 4, 5 pi over 4, and 7 pi over 4. My derivative in its most cleaned up version was this cosine of 2x, so let me label that. And I'm going to do one thing that's slightly different on this example. We were given this interval 0 to 2 pi, so to make sure that I stay within that interval when I'm doing my test points, I'm going to put a 0 here and a 2 pi here. And those aren't technically critical numbers, but it's just a reminder of where I want to start and stop. So let's test anything between 0 and pi over 4. So you could try something like pi over 6, okay? So if we tested pi over 6, that would be cosine of 2 times pi over 6, which is cosine of pi over 3. And that's in quadrant 1. Pi over 3 is in quadrant 1, and cosine is positive in quadrant 1. So this would be plus. Now we need to pick something between pi over 4 and 3 pi over 4. So something like pi over 2. So if you were to plug in pi over 2, we would get 2 times pi over 2, which is going to turn into a pi, and cosine of pi is -1, so this will be minus. If we try something between 3 pi over 4 and 5 pi over 4, okay, keep in mind your unit circle. Here's pi over 4, here's 3 pi over 4, here's 5 pi over 4, and here's 7 pi over 4. So something between these two would be like pi. So let's try pi. If I plug that in, I would get cosine times 2 pi, and cosine of 2 pi is +1. So this is back to a plus. Now we need to test something between pi over 4 and 7 pi over 4, so let's try 3 pi over 2. 2 times that would be 3 pi. And cosine of 3 pi is the same as cosine of pi, so that's negative. So we're back to a minus sign. And finally, we need something between 7 pi over 4 and 2 pi, so maybe like 11 pi over 6, that would be right here. So if I tried 11 pi over 6, 2 times that is 11 pi over 3, and that is going to be just shy of 2 pi, which would be 12 pi over 3, and that is quadrant 4, and cosine is still positive in quadrant 4, so this would be back to plus. So all of my signs alternated here. So let's just put our final answer down. Therefore, where do I increase and where do I decrease? Well, I increase wherever I have these pluses. So this one would be from 0, and I am including the 0 because I'm including it here, up to the pi over 4. Now I'm not going to include the pi over 4. Then from pi over 4 to 3 pi over 4, I decrease. Use parentheses around all these interior critical points. I'm going to use brackets around the two endpoints, the 0 and the 2 pi. Then between 3 pi over 4 and 5 pi over 4, I'm back to increasing. And then after 5 pi over 4, I'm back to decreasing. And then after 7 pi over 4 up to 2 pi, I'm increasing. So those are my intervals of increase and decrease. And finally, let's figure out our relative extrema. On the left here, I go up and then down. So that's a max. Here I go down on the left, up on the right. So this is a min. Here I go up on the left, down on the right. So this is a max. And here I go down on the left, up on the right. So I have a min. So my relative maxes are at pi over 4 for the x and 5 pi over 4 for the x, and my relative mins are at 3 pi over 4 for the x and 7 pi over 4 for the x. And to find these y values, we're going to go back to our original function, which was sine x cosine x. That was what our function y was. So if we were to plug in pi over 4, sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. When I multiply those together, root 2 over 2 times root 2 over 2 is just 2, and 2 times 2 on the bottom is 4, so this is a positive 1/2. Now, if I go to 3 pi over 4, that's quadrant 2. So if I change these to 3's, in quadrant 2, the cosine is negative, but the sine stays positive. So this would just change to a minus 1/2. If I go to 5 pi over 4 and make these 5's, now I'm in quadrant 3, and both sine and cosine are negative, and a negative times a negative is a plus. So now we're back to a positive 1/2. And finally, if I went to 7 pi over 4's, that's quadrant 4, so sine is negative, but cosine is positive, so we would be back to a negative. So this is negative 1/2. Okay, here's our final information. And we're not going to bother putting it all into a graph for this one because they just asked for the intervals of increase and decrease and the relative extrema. All right, that concludes our lecture on the first derivative test. Good luck.